Alright.
The actual like definition of it is September.
Well, I think it's time to get started. Let me begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you to bless our work today and the weekend, which is about to start. I thank you for the nice weather today, and help us to avoid the CFAs, Lord. In your name I pray, Lord Jesus. Amen.
Hey.
Wait a minute. Are there any CFAs here? I don't think so. I think so. Let's see here. Oh, no, you're not CFA. Nice try. Let's see here.
I almost had you.
Huh. Did this not get passed around yesterday? If you'd add another day, let's do it. This is a twofer, apparently. All right. So you guys can get out a piece of paper. Everybody get out a piece of paper. Put your name at the top. Put your notes away for a moment. Problem? I'm not. Define series. I would like the definition of series. You got a minute? Do 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 do. Do 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 do. 30-second warning. I don't usually give 30-second warnings, but this is a short quiz. All right, time's up. You can put your name on there and pass it up, please. Thank you. Pass them up. Pass them up, please. Stop writing. Pass them up. Thank you. Thank you. Ahem.
Sorry, I'm
What did you do? Oh, I thought you just
It's an extra piece of paper. Come on,
It was just like,
All right, let me see what we got here. All right. So yesterday we defined series. Let's see. Do we have the definition down yet? Nope. 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 70%. Nope. Yep. Nope. Nope. That's a nope. Let's see here. Ooh. No. 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 possibly. It takes me a while to read that handwriting. Let's see here. Nope. Wait. Debatable. Let's see here. Yeah, debatable. Nope. I mean, closer, but nope. Nope. Pretty much. Hey, you guys are doing better than usual. Usually I do this and there's like one person.
Let's go.
Yep. Actually, I have hope for you guys. This is not...
So before, like yesterday, you didn't have hope is what you're saying?
Oh, I've done this in the past, and I've gone through, and there's been like one person.
We had like 5 points less than
I will think about that.
10 points.
But I would encourage you that this might happen again, and maybe next time I ask this quiz, you'll, have the, you have the, you have the answer. Yeah, that's very green. Let's see here. No. Well, yeah, there's another. Hey, hey, you guys, 1, 2, 3, 4, 5, 6, 7. Basically 7 people of the, what? Were there about 35 in here, maybe? What's that? I'm not going to name who got it.
Come on, we want to know. You want to know who to befriend.
Well, I mean, in a different time, yes, we would have, I would have brought 30 dunce caps and had the 30 people who got it wrong wear those caps, but, we're not
Tomorrow.
generally frowned upon to do those kind of things anymore, right?
Not tomorrow. Monday. Whatever.
Monday. You will have another chance on this quiz, probably Monday. So hopefully then you'll know. All right. So, what's that?
Yeah.
Oh, sure.
Find it or like, so we know if we got it right or wrong.
So the definition is just this. The sum, I said k equals n naught to infinity of a sub k is equal to the limit as n goes to infinity of the sum k equals n naught to n of a sub k. So that's the definition in a nutshell. Now, a more complete definition would say something like the sum of the series is said to be the limit of the sequence of the partial sums when it exists. If this limit does not exist, then the series is rather said to diverge. But that's the heart of it. All right. Now I wrote a half a board of words, right? But at the end of it, I told you more briefly this is the definition, and some of you took that to heart and told me back that this morning. So that's good. Others who are still absorbing it, and that's also fine, but you do need to learn that soon because that's kind of at the heart of everything we're doing. So moving on here, this is our first theorem for today. Suppose, all right, that the sum of AK is equal to A, and the sum of BK is equal to B, all right, where big A and big B are elements of the real numbers, and C is also a real number. So when I use this notation, I'm just abbreviating, right? So I do mean for these to be infinite series. It's just, so the more full story would be this is that. I'm just not writing all that here for the moment. Then, a couple things. Number one, the sum of AK plus BK is equal to the sum of AK plus the sum of BK, right? And number two, if I take the series formed by multiplying each term by that constant C, well, it's the same as C times the series. In other words, I can pull a constant out of a series and I can break a sum up. All right. I said, in other words, the sum and scalar multiple of summable series is summable. Similarly, I would mention that if the sum over A diverges, then the sum over B converges then let me just write it down. So also, if the sum over AK diverges, all right, and the sum over BK, let's say, converges, then you get a couple things. You get the sum of AK plus BK and the sum of C times AK. Both of these also diverge. All right. Now, how would you prove these things? So let me go through the proof here for a minute. Let's see here. So essentially, just this. Observe that the sum k equals, let's say, n naught to n of AK plus BK, right, is equal to, and I can throw a C in here. Well, that's equal to C times the sum of AK plus the sum of BK. And here we're going K equals n naught to n, K equals n naught to n. So what I'm writing down at the moment is just something that's true for finite sums, all right? So the finite sum breaks up across addition, and you can pull constants out, right? So this is the fundamental identity that I have to work with. Now, if I assume, right, if I assume that these series in the theorem converge, right, that they're summable series, what does that mean? What's that say about the limit as n goes to infinity of what I have right above here? Well, it's going to be C times the limit as n goes to infinity of this. So I'm just using limit laws, yeah, for the sequences, paired with the identity that I have right above for the finite sum. So much writing. Let's see here. So then if those series converge, then what do I get to say about those limits? 5 of you know. Right. It's not too late. The other class I had to do, in classically there was one semester I had to do that quiz 5 days in a row before I finally got 90% of the people to know the definition. It took 5 days. How many days will it take with you guys? Do you think I'm just going to keep doing it every day?
23.
What's that? 23 days. Whoa, that's kind of dark. It's kind of dark. I don't know. So guys, listen. This limit goes to what? In the language of the theorem, this is A, right? In the language of the theorem, this is B, right? Those limits converge, and this is equal to CA plus B, right? But that's exactly C times the sum, K equals n naught to infinity of A sub K plus the sum K equals n naught to infinity of B sub K, right? And I'm using the limit laws, right, which say that you can break a limit up and a limit of a sum up and the sum of the limits provided what? You need that the subsequent limits exist, right? So that's number 1 and number 2, both at once. I did it both at once. Do you see how I get both for 1? It's a twofer. If you put C equals to 1, you get number 1, right? If you put C equals to 1, you get number 1. if you put the B series to the 0 series, which we know converges, we talked about that last time, right? Then you get number 2, right? Number 3 is actually pretty obvious if you just think about the formula that I have right here, right? Think about this. If the partial sums for A diverge, right? And the partial sums for B converge, that means that as n goes to infinity, this partial sum blows up. Because there's no way something finite can temper something that's going to infinity, right? Like it can't cancel it out. If both A and B are both infinite, then that's more complicated. There could be some kind of systematic cancellation, all right? Like with the telescoping series, that can happen. Anyway, so that's that. So there's our first theorem for today. And now let's use it. Any questions before I go on, though? All right, I will try to reserve about, let me try to make sure I make a point of about, I don't know, 10 minutes before the end of class. I want to get the projector out and talk about the homework problems, which ones are reasonable for you to do at this point versus which ones are too hard. Yeah, so too hard in the sense of we don't currently have the technology to solve them yet. So here's example 1 for us. So you guys help me out with this one. Here we're facing the sum k equals 0 to infinity. K equals 0 to infinity of 4 to the minus k times 2 to the k plus 3 to the k. Actually, let me not keep writing this sum every time. What we should do is we should focus our attention on the actual term and try to understand what's going on there. And then, so what's my? Let's just look at this expression. How can you guys help me out here? What are we up against here? 4 to the minus k times 2 to the k plus 3 to the k. Can you rewrite that? This is what? 1 over 4 to the k, right? Times 2 to the k plus 3 to the k. Which then algebra says what? That's, what's that? Well, that is true. It does look like it might be infinite. I mean, it does look like it's the form 1 over something that's really large. That has type 0 times infinity. You're right. So on the surface of things, it looks like it might diverge, right? But I don't think it does. See how this goes? So this is 2 to the k over 4 to the k, right? Remember, when we have 0 times infinity, that doesn't mean the thing diverges. That just means you've got more work to do. You have to sort it out, see how it goes, right? That's an indeterminate form. Now we're starting to get something that's a little bit, well, now it's infinity over infinity plus infinity over infinity. But what if we just make this algebra step? That's 1/2 to the k plus 3/4 to the k. Yeah.
Would that be?
Mm-hmm. So yeah, the first thing to think about then, once you have the expression to a reasonable form, is, hey, does it pass the kth term test, right? If the kth term in the series that you're summing, if it doesn't go to 0, game over, the series diverges, right? We proved that last time. How about this? What happens as k goes to infinity? Yeah, both of those terms go to 0. In fact, isn't it the case that this series and this series actually are separately summable? I'll write out a couple terms. So you've got 1 plus 1/2 plus 1/4 plus dot 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 dot. This one is 1 plus 3/4 plus 9/16 plus dot 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 dot, right? So the last series we saw last class in terms of a hot dog stand, you may remember, we worked out that the answer was 2, right? If a man and infinitely many of his friends want to buy a hot dog, then half a dog, then half of a half of a dog, then a half of a half of a half of a dog, then and so forth. It's my stupid example. But yeah, that's a geometric series with ratio 1/2, right? So that's convergent. it converges to 2. This one, I'll work this one out. This one converges to 1 over 1 minus 3/4, right? What does that equal to? 1 over 1/4, right? So that's equal to 4. So, thus, the sum k equals 0 to infinity of 4 to the minus k times 2 to the k. I really should have just given this thing a name so I didn't have to write all this again, right? It's equal to the sum k equals 0 to infinity of 1 over 2 to the power k plus the sum k equals 0 to infinity of 3 over 4 to the power k, right? And we just, this is by geometric series, this is 2. By geometric series, that's 4. So in fact, this series that we're looking at is convergent. And in fact, its sum is 6. Where I've done what? I've just used our theorem that we proved today, part 1, right? So that's an example. All right, so moving on here. To go over here. So this, there are theorems in here which I have to like chide you guys to remember. Like, learn this theorem, get it in your system. This is not one of those. Like, pretty much you guys latch onto this one pretty quickly, and it's never too much of an issue. The main thing with this theorem is to not use it incorrectly. All right. So keep in mind that when both of the resulting series are both infinite, you can't use this theorem. It's just not true in that case. All right. I can show you an example of that. Here's why the series is not true. I actually don't have an example right offhand. Let's hear. Let me move on here. Integral test. So let us move on to the integral test. So here's essentially the. First of all, I need like a sort of a theorem before it. If the sum k equals n naught to infinity of a sub k I'm debating whether I want to write all this stuff out here. I'm going to say no. I'm going to project this a little bit later, guys. Sorry. So I have a more full proof in the notes. I want to just show you a more intuitive proof for class time, okay? So this is essentially the idea. If we have y equals f of x, right? And this is continuous, positive, and decreasing, right? If it's continuous, positive, and decreasing, what does its graph look like? And let's say for x greater than or equal to 1. I saw somebody make a motion, so it's something like that, right? It keeps going down, and it looks something like this, right? Now, what if you study a series where you have, you can draw a picture, something like this. So this, what I'm drawing, would represent these boxes, the area of these boxes. What could they represent? Like, what would this point be here? Maybe we're at, this is 1, this is 2, this is 3, this is 4, and so forth, right? So the area of the first box we could say is A1, right? The area of the second box would be A2. Notice that the width is 1, so the height defines the area, right? Length times width is area. We know this, yes? Okay, good. So this would be the area A3, A4, and so forth, right? So, okay, then what? Well, this suggests what? That the sum, right, k equals 1 to infinity, right, of a sub k, yeah, well, we could compare that to the integral. What would the integral look like? How would that relate to the integral of the function here? Like if I was to talk about, let me just throw it up here, the integral from 1 to infinity of f of x dx, right? Yeah. Yeah, I would tend to agree with you, but it's not quite right? Because the integral would give us this right here, right? Did you see what I'm talking about? Do you guys see it? The area of the integral is inside this blue dotted line, right? So they're not quite comparable because what? I mean, I could definitely say that the series is less than the integral if I do what? Go from 0 to infinity? Well, if I could integrate from 0 to infinity, but I'm not gonna do that. But fair enough, you could do that. That would be. He's like, well, just integrate from 0 to infinity. Fine, but you know, maybe your integral, maybe your function has something unpleasant happening at 0, so you don't want to do that, right? There are functions like this whose integral from 1 to infinity is finite, and yet the integral to 0 blows up because they've got some vertical asymptote at 0, which is not nice. So you don't want to do that. But there's a simple fix. So if you take this series, right, and you just subtract this piece off of it, yeah? So if I say this whole thing, right, minus a1, that is what? That is definitely less than or equal to, I mean, it's not going to be equal. With my picture, it's strictly less than, right? Agree, disagree? What does this mean, intuitively speaking?
The integral is convergent, then the series is convergent?
Right, that is exactly what it says. It says that if the integral converges, then the sum, the series converges. Right. Now, I have a more nuanced version of this argument in the notes, all right? So we'll project that, and I'll go through it here after we've applied this a little bit. But yeah.
So can you explain why you subtracted a1?
Because the area under the function is the blue piece, and this a1 has nothing to do with that.
Like the function that you chose to take the integral of?
Yeah, yeah. And what's the relation between the function and the integral for this argument to make sense? What am I assuming? What's the deal? F of n equals to what? A sub, yeah, A sub, well, I did an n, but I got, your heart's in the right place. So, yeah. But yeah, we could put a k there. Yep.
So, when you write that series, you just kind of like ignore the change in x because it's assumed to be 1? Because for it to compare to the area of the curve, it's giving you like height values?
Oh, I'm not saying that that's a Riemann sum. I mean, this is a series, so.
Right. I'm just saying that like the series gives you the sums of all basically the heights that you drew, right?
Yeah, but those series are the area because,
Are they?
well, this is length 1, length 1, length 1, so the height is the area.
Okay, yeah, that's what I was asking.
Okay, good, yeah. So if you can do this, you can also make another picture, right? Check this out. So actually, let me do something hideous and, no, I'll draw a new picture. You know, sometimes I try to draw both of these on the same picture, and it goes badly. So let me just do it again. So you could also be like, well, why didn't you draw the picture the other way, right? Because you could have done this. right? Well, I should have made this function bigger, my bad. But anyway, here, this would be a1, right? This would be a2. This would be a3. Again, this is 1, this is 2, this is 3, right? This is 4, and so forth, right? So what does this picture suggest? Again, this is a graph y equals f of x with continuous positive decreasing for this whole discussion to make sense. Well, this suggests that the series, right, the sum k equals 1 to infinity of a sub k is what? It's greater than or equal to what? The integral from 1 to infinity of f of x dx, right? Can you see that? So now I've got the I'll just shade it for the sake of uglifying things here. That's the area of the integral. The area represented by the series is above it. So what does this tell you?
The series would be larger.
How about this? If the integral from 1 to infinity of f of x dx diverges, right? Then what? The series diverges. And so that's the integral test. The integral test says that basically if you have a continuous positive decreasing function whose values match the terms in your series at integers, all right, then the integral shares the fate of the series. If the series converges, the integral, if the integral converges, then the series converges. If the integral diverges, the series diverges. Just the same. Does that make sense? It's relatively simple, except that its application is kind of a hassle, as I'll show you shortly. Ooh. Yeah, see, so I'm going to, if you don't mind, I'm going to, yep.
Should that be k equals 2?
No, this is 1.
Because would it be the same?
Well, you could, you're right. Fine. I'm not disagreeing, but this is literally the sum k equals 2 to infinity of a sub k. That is true.
The bottom one.
Ooh, no, it starts at 1.
But if they're both the summation, then why do they look different? You see what I'm saying?
Because I've drawn the picture differently. I flipped this box over here. It's the pictures. You can draw both of these pictures. They're genuinely different. They give you different estimates. So if you look at the left endpoint rule versus the right endpoint rule for delta x being 1, they give you different. They give us different sums. And all right, so come on, full screen. So I see we have some CFA people in here. Is it?
Yeah, I'm just here with my son over there.
Oh, you're not coming to no.
I would love to, but we speak a different language.
Let's see here. So here's the full proof, guys. I start by proving this dichotomy theorem for positive series, which basically just says this. If you have a series that has a sequence of partial sums, and that sequence of partial sums is bounded above, all right, then the series converges by the monotonic sequence theorem, because it gives you a bounded monotonic sequence. If you have a series of positive terms and you're adding terms, that means the series is that means that the sequence of partial sums is increasing. So if you have an increasing, if you have a monotonic increasing sequence of partial sums and it's bounded above, then by the bounded monotonic sequence theorem, it converges. And if it's not bounded above, then it diverges. So this is called the dichotomy theorem for positive series, and that's at times useful. I drew these pictures for an arbitrary function over here. Here's kind of what it looks like for 1 over the square root of x. Again, we can draw both of those pictures. And so my specific point here is that these inform us that if we look at, oh man. Oh, no, it's fine. So in view of the left picture, the integral from 1 to infinity of 1 over root x is infinity. It follows that the series k equals 1 to infinity of 1 over root k is also infinity. On the other hand, if that's 1 over x squared, we can calculate the improper integral from 1 to infinity of that. It works out to a half. And that means that the sum k equals 1 to infinity of 1 over k squared likewise converges. And more than that, it has to converge to something less than a half. All right, so this is the integral test. It says just what I just said. And the full proof of the integral test is given here. Oh man, this laptop gives me fits. But it's better than my other laptop because at least this one doesn't have a permanently depressed space bar. I mean backslash. I was thinking about swapping out the keyboard, and then I watched the YouTube video on replacing the keyboard and decided that it was time to replace my 9-year-old laptop. So, yeah. I bought it for my wife, but anyway. She used it for like a day, then she's like, the screen is too small. I'm like, so it's mine. It was $1,000 when I bought it, so it was pretty nice, but that was 9 years ago. So anyway, so here's the full theorem. Again, we have a function matching the terms in the sequence. All right, so I've already said that like 3 times now. Fine, but the main thing here is if you look at Cn, I say let Cn be equal to the integral from 1 to n of f of x dx. This defines a sequence. All right, it defines a sequence, if you will, and you can compare that sequence to the nth partial sum of the series. And then that can be compared to another sequence, which is formed by integrating from 1 to n plus 1, all right, of f of x dx. And I'll call that b sub n. So if you look at it, you've got a sequence below, a sequence above, and then what do you think the argument's going to be? Squeeze theorem, right? Basically, it's kind of that. So the integral from 1 to infinity converges, then that implies that, well, anyway, I'll let you guys read all this. So there's the proof. I let you read it, okay? It's not especially interesting. It's pretty much what I've just told you already. Let's look at the examples. That's really more interesting here. So I guess I should check my, camera here. All right, so to apply the integral test is a kind of annoying thing because the integral test, excuse me, just got to check on my, it's the one part I have to do. There we go. The integral test, there's a lot of terms and conditions here, right? So I'm going to apply it to 1 over 1 plus k squared, all right? Like the sum k equals 1 to infinity, 1 over 1 plus k squared. That seems like a good one for the integral test because I know how to integrate the corresponding function of x, right? Like integral of dx over 1 plus x squared, well, that's inverse tangent, right? We know how to integrate that. So maybe integral test is a good choice here. In fact, it is. But if you're going to use the integral test, technically speaking, you do need to actually check on the preconditions of the theorem, which is kind of a hassle. So I let f of x be 1 over 1 plus x squared. I just say, okay, so if x is greater than or equal to 1, it's pretty clear it's positive and continuous. I'm not going to belabor those points. But I do need, if you're using the integral test, you do need to say those words. Those words must be spoken. Otherwise, I must take away points. Okay, because that's part of it. Not a lot of points, but something, yeah? Okay, so to see that f is a decreasing function, what's oftentimes convenient is to look at the derivative, right? Because if we can show the derivative is negative, that means it's decreasing. So df dx here, quotient, what's this called? Quotient rule, right? Minus 2x over 1 plus x squared. Well, that's manifestly negative, right? Because you're taking something that's negative for x greater than 1, and you're dividing by something that's non-zero and positive. So definitely less than 0. So hooray, we can use the integral test because this is a continuous positive decreasing function which matches our given series. And then, oh, come on, really? Well, I'm not sure what happened here, but I think, well, I'll fix that before I post this again. Sorry, guys. As you know, these are fresh. So this is also supposed to be over here, obviously, right? And it's good. At least we don't have visitors or anything today. But the days when there are no visitors, I make no mistakes, right? And you guys are like celebratory. Every class ends with you guys clapping for me and saying, "Please don't end class. Go on. Tell us more about calculus, please, please." No? Yeah, you pray for it? Okay, good. So we take the limit as t goes to infinity of inverse tangent of t. Now, you guys know that that's pi over 2. Inverse tangent of 1 is pi over 4. So this minus that, pi over 4. Now, that doesn't mean that the series converges to pi over 4. What it means, all right, is that it converges to some number less than pi over 4, actually. All right? So anyway, this converges by the integral test. Yes, sir?
The formula on the board, you have like less than equal to or greater than equal to, but on the notes, you just keep saying less than. So can it be equal to, or is it just like this with these?
I think it's strictly less than, but if it's strictly less than or equal to is not wrong.
Okay.
It's just not, you know. So here's another one. This one, I have 2 over 2k plus 7. I verify that the function's positive, decreasing, continuous, all right? Apply the integral test, and, come on, again? What's up with that? Well, at least I'm consistent in my inconsistency. So, like, this is supposed to be over here as well. Anyway, so that diverges, and as such, this diverges by the integral test. Now, we will soon find a better way to do this problem, and the last problem, actually. So let me go on here. So example 4.8 is important. Check this out. So if p is greater than 1, then you can calculate the integral of, hey, I did it this time, yay. So integral of dx over x to the p is the limit as t goes to infinity of this, right? Which we can do this integral. The integral is minus 1 over well, this p minus, there's a typo here as well. This is supposed to be multiplying this, but it doesn't change the outcome, right? Because if you got p minus 1 times this, the point is that this piece still dies because t goes to infinity and that vanishes. Because we're assuming that p is greater than 1. Since p is greater than 1, that means this is a positive power. If you have 1 over t to a positive power as t goes to infinity, that goes to 0, which just leaves you this term like so. So what that then tells us, since this is also a, as you can see, decreasing function, that tells us then that the sum k equals 1 to infinity of 1 over k to the power p is convergent. This is something we need to remember, all right? So this is part of what's called the p-series result, all right? Let me show you the rest of it. Come on. Come on. Go down. I said go down. Well, you know, I missed my page down button. There it is. You got to press FN to get the page down button on this dumb thing. I guess I shouldn't complain. It was free. I'm still going to complain, though. Let's see here. OK, so all right, so this is a special case, right? Dx over x integrates to log. So, but it is a positive decreasing function on 1 to infinity. Therefore, the integral test applies. And it applies to show us, because the integral from 1 to infinity diverges, it follows that the harmonic series, sum k equals 1 to infinity of 1 over k, is likewise divergent. This is the proof of the example I mentioned last class being a counterexample to the kth term test telling you anything about convergence, right? Because here it is. The series has term 1 over k goes to 0, and yet that series diverges, right? So we must distinguish in our mind between the convergence of the kth term as a sequence, like the limit as k goes to infinity of a sub k, versus the limit of the sequence of partial sums. These are separate logically distinct limits which we must think of as separate. All right? So that's the fundamental confusion in here, is you guys think of those limits as being the same thing, but they're not. But anyway, that's the harmonic series. Now, if you have p is between 0 and 1, then it's easier to show that that integral is, again, the integral diverges. And so this brings us to the p-series result. So here's the p-series result. The p-series is simply this. The sum over 1 to sum k equals 1 to infinity of 1 over k to the p is convergent if and only if p is greater than 1. Otherwise, if p is less than or equal to 1, that is a divergent series. So this is very nice, right? Because what this means is after this point, I don't expect you to do the integral test for this. I expect you to reference this theorem, right? So the integral test we do once, we get it over with. We've done it. Now we own these. We've owned these truths for going forward. Okay. So now there's more. This is actually pretty neat. If you take a harder look at the pictures I drew, you can actually come up with the following estimate. The integral from n plus 1 to infinity of f of x is less than or equal to s minus Sn of the integral from n to infinity of f of x dx, like this. And so what that means is you can bound the error in the nth partial sum like so. So if you use that, we can kind of take a look at the integral, sum k equals 1 to n of n squared. So the nth partial sum would be this. You could ask the question, how many terms do you need to sum in order to know that you're within 0.1 of the real answer, right? Because we know this converges, it's p equals 2 series. And so I calculate this integral, I get 1 over n. So apparently we should take n equals to 10, that should be enough. So here's the sum of the first 10 squares reciprocals, which is apparently 1,968,329 divided by 1,270,080. I did not do that with a calculator, right? What did I use? Brain? No, of course not. I used Wolfram Alpha. Come on, guys. So Wolfram Alpha is very handy for this kind of thing. 1.5497. Now you might say, well, how do you know what's the exact value of the series, right? Well, I know that because, because Euler knew it. Who's Euler?
Some dead guy.
Some dead guy. So disrespectful. Yes, but yes, he is dead, and he was a guy. It's true. You got me. But yes, he's an 18th century. I think he calculated this in 1750, something like that. He showed that the sum of k equals 1 to n, that's supposed to be infinity. My bad. I'll fix it. Is actually pi squared over 6. So this sum of reciprocal series actually sums to pi squared over 6. And so you can compare the approximation of keeping the first 10 terms to the actual answer. And indeed, I get less than 0.1. I get 0.0952. So the estimation theorem works. And man, if you wanted to, you could sum the first. If you wanted to get within 0.01, you'd have to take the first 1,000 terms to get that close. So anyway, this is kind of just for fun today. But so I said I'd tell you guys something about your homework. Let me do that. So let's see here. We're on mission 2, right? And you guys have already done up through problem 60, so that's good. 61 you can do, 62 you can do, 63 you can try. 64, yesterday I told you part A is dead to us, right? Because it doesn't make sense. Problem 65, I have worked in class. You just got to stitch all those stories together. It's also in the notes, which I think I've already posted, but I need to fix before I post again. This one's easy. This is an easy problem because that has a limit which is not 0. Work it out. Why does that have a limit which is not 0? Figure it out for yourself. I can. Well, yeah, I can. Yeah, I can.
I don't believe you, right? What if you can prove
Well, it's a chance I'm willing to take. So this one here is geometric. Just figure it out. That's geometric, actually. But you need to figure out why that's geometric. So since it's geometric, I think that one has convergent. This one here is just in-your-face telescoping, so you can do that one. 68 is a telescoping series. 69, oof. 69 looks like it's above our pay grade at the moment, unless the limit's not zero. Unless this limits to something not zero, but it's got a k factorial in the denominator. I don't think things are going to go well for us. This one here, you should be able to do, or you should be able to try, I should say. I don't know right off the top of my head about that one. Let me not say anything. This is telescoping. You can do this one. 72 you can do. You got to do partial fractions on it. You can do it. It's telescoping. This one here, goodness. Oh, I think this is actually integral test. So this is actually a good integral test problem, because this is, if you replace k with x, you can do this integral. And I think this is an integral test problem. Goodness, I don't know about this one. That might be telescoping. I would wait on 75. I would wait on 76. 77 you can try if you understood what I just presented about the error theorem, but I can talk more about the error theorem again if you guys want. Anyway, oh, I'm sorry, I've gone over time, my bad. So I'll shut up. There is another problem at the end. It's about the